Can you see the screen, Ali?
Yes, I can see it.
So now we are looking this question. This is superposition, and the second chapter we couldn't complete, and definitely this is going to be a problem tomorrow. But as I said that you can't damage a chapter of this level, and you cannot do it with a very high speed. Even we did it in a very high speed, still this is not easy to complete it. So I'm putting a question for our revision. This is June 12, 6. Use the principle of superposition to explain the formation of a stationary wave. It's a 3-mark question and a full memory question.
So first we'll tell the principle of the superposition and then what stationary waves are.
No, I don't think so. You can directly say that a stationary wave is produced by the superposition of the incident wave and the reflected waves. As the marks are 3, then you can say that it is the algebraic sum. It is the algebraic sum of the two waves resulting in the formation of nodes and antinodes.
The last chapter was still like a bit more manageable than this one.
Yes, but if you can save the, you can save the paper tomorrow if you give more time to learn the wavelengths, to learn the memory work, and try to remember the stuff, because this chapter is overall very challenging. And if you haven't completed it, then you can imagine it is how much dangerous. Describe an experiment to determine the wavelength of sound in air using stationary waves. We just did it yesterday, and I had put a ruler, if you remember, like this. There was a reflecting surface, there was a loudspeaker, and there was a microphone. Do you remember it now?
Yes, I got it. In which like the waves were produced and they hit the and got reflected back, and then there was
Yes, it
superposition of.
was. Yes, you send a signal like this. The signal strikes, and the signal comes back, and it forms a series of node, antinode, node, antinode, and you make this with me so that you get a memory. Now the microphone was connected with a CRO. Have you copied it?
I have copied it.
I have shared the wavelength table with you again. And now what was the method? Do you remember that we have to move? We have to move the microphone, and we have to locate the position of node and antinode. How we can locate the position of node and antinode using the CRO?
The mean displacement and the least displacement.
Yes, you can see this one. This is the output from a CRO. Once you locate two successive nodes or two successive antinodes, the separation is lambda by 2. So if you double the distance, this is d, so d will be equal to lambda upon 2. So lambda will be equal to 2d.
Okay, and then this like the signals will be zero at the node and anti-node, the signal will
Yes.
be max.
So what you do using the microphone, you locate nodes and antinodes successive, you take their separation and you double the separation. You double the separation to get wavelength. Now we come to this part. The variation with distance x of the intensity of a stationary sound wave is shown. On the x-axis of the figure, indicate the position of all the nodes and antinodes. So I just made this sketch for you here. So you can tell me that this will be node, this will be a node, this will be an antinode, this will be an antinode, and this will be a node. Now, the speed of sound in air is 340. Use figure 6.1 to determine the frequency of the sound wave. What's the formula? V is equal to F lambda. F is equal to V upon lambda.
So we'll take lambda as 30 centimeters
How 30?
because from one trough to another trough is like almost 30.
No, but you're making a mistake. It's a node-to-node game. It's not a wave. It's not a transverse wave.
Okay.
And node
Lambda by will take. No, no, by no.
Sorry, I lost the connection for a second, and we were here, and I had found that the separation is 34. What should I do now?
So we'll half it.
Look, the calculation.
Okay, we'll double it.
Yes. Now you have to remember, it is in centimeter. He is playing again, and it's meter per second.
The answer is coming as 500 hertz.
500. Now, monochromatic, this I haven't done with you. So I don't think so we can discuss it effectively. Anyways, this is an important question. This type of questions are very important, and you should try yourself a bit. Let's see how much you can get out of it. We can try this one. The figure shows an arrangement for producing stationary wave in a tube that is closed. I hope you remember this thing, closed tube. Explain how waves from the loudspeaker produce stationary waves in the tube. The waves goes up like this, strike and comes back like this. This is reflection. So you tell examiner that it is a type of like this. It is a type of superposition of incident and reflected wave. Let's try to make a better diagram. The tube is so long like this. Now it's better. And I hope you remember this is antinode and this is node.
Yes, I remember this one. We did it yesterday in the class.
Yes. So you should tell the examiner that it will be a superposition of the incident signal and the reflected signal. Now you see the next one. One of the stationary waves that may be formed in the tube is represented in figure 4.2. Describe the motion of the air particle at the tube at point P. Let me mark again. This is node, this is antinode, this is node, this is antinode. Antinode is the point of maximum displacement and node is the point of zero displacement.
So the velocity at P will also be zero and at S will be maximum.
Sorry?
So the velocity will also be zero at the node.
No, velocity can't be zero. You talk about the displacement. They do not move. Node means the particle doesn't move there. It will like a knot. And antinode is the point where particle moves with full excitement.
So we'll say maximum and displacement and zero displacement.
Yes. The speed of sound in the tube is 330 and the frequency of the wave from the loudspeaker is 880. Calculate the length of the tube. This is a bit tricky part, and you just have to remember that he's talking about this figure 4.2. And I mark the tube length as L for you. This is the length of the tube. Now, do you remember I explained you that this is the only calculation which comes that what is the length? So now you can tell me what is the length. It's node to antinode, then a node, then an antinode.
So first it's lambda by 4, then lambda by 4, and then lambda by 4.
Very good. So it means it is actually 3 times lambda by 4. So can I write it 3 lambda upon 4?
Yes.
Good. What should I do now? He says calculate the length. I got this point that L is equal to 3 lambda upon 4. Formula says V is equal to F lambda. Lambda is equal to V upon F. Lambda is equal to V upon F. So what I can do, 3 V upon F upon 4. What is V?
The velocity,
No, number.
330,
Yes. And what is frequency?
880.
Good.
It's 0.28 meters.
0.28 meter. The figure shows a string stretched between two fixed points. The vibrator is attached near end P of the string. End Q is fixed to a wall. The vibrator has a frequency 50 and causes a transverse wave to travel along the string at a speed of 40. Calculate the wavelength. The first part looks simple. V is equal to F lambda. Now, this is the case.
It's 40 divided by 50, which is 0.8 meters per second. 0.8 meters.
0.8. Should I take 0.80? I think 0.8 is fine. One significant. Explain how this arrangement may produce a stationary wave on the string. This is their favorite question. And you should always remember that a stationary wave is produced by the superposition of incident and reflected waves. It's a memory to build. Right? Now, we move forward. The stationary wave produced on PQ at one instant of time is shown. Each point on the string is at its maximum displacement. I make a stationary wave for the simplicity, and you can then tell me if I this is now. So we can make this antinode, node, antinode. Oh, I mark, acha, 2 marks is there. Okay, fine. Use your answer in A part 1 to calculate the length of the string PQ. Again, the same question. This is the length. Can you first find how many lambdas are there?
This is 3 lambda over 2.
Very good. 3 lambda over 2. And how we find the length now? Has he given us any hint? Okay, he has given us the wavelength. Good. So L is equal to 3 lambda upon 2. L is equal to 3 lambda upon 2, and you know the lambda is 0.8. So 3 into 0.8 upon 2.
It is coming as 1.2.
Good. On figure 5.2, draw the stationary wave at time t plus 0.5 millisecond. Like this, t plus 5 millisecond. Now we should know before solving this part, even it's a small part, but you can see the marks, 3 marks, and it means there is some issue. So first I find the time period. It is 1 upon f. And I have to see the frequency is 50. So I will say 1 upon 50. Can you solve this?
It's 0.02.
I multiplied with 1000 to get it in millisecond. I got 20 millisecond. So once I get 20 millisecond, he is asking me for 5 millisecond. So if I make a ratio 5 upon 20, it will be 1/4. It means it is 1/4 of, it is 1/4 of a cycle. It is 1/4 of a cycle. So now it is possible to draw because he's talking about 1/4 of a cycle. Now this is the wave. I am rubbing it so I can get it in my original form. This was the original signal. So where it would be one cycle. One cycle is one complete loop, and it comes down, it is one cycle. I shared it for you. This is one cycle. How much I need?
1/4 cycle.
Yes.
So it will be half of the first cycle, first loop.
Yes, this is lambda by 4. So I have to draw, because he's talking about stationary wave. This is a tricky part. He's talking about stationary wave. He says, draw the stationary wave. Now, how I can draw a stationary wave? When examiner says to draw a stationary wave, remember, you can draw a horizontal line as I'm drawing here. Look, this is a stationary wave. because stationary wave is actually on zero axis. It appears to be up and down both, but it is not actually up and down, it is a straight line. Okay, so it's time for you to do some more practice, and you have to revise the definitions. I think you can manage, but you have to remember those wavelength table I have posted for you again, and you must have to remember all the formulas. And let's see what happens. I couldn't do a question on Doppler effect with you, but I think you remember the formulas. I will try to post you again. Do not forget to do formula on Doppler effect. Okay. Now we stop here and let's see what happens tomorrow. Allah Hafiz.
Allah Hafiz.